I can hear you, sir. Hello, all. A warm welcome to Enter Speech. And then I was very sorry for not attending to the conference because of these COVID reasons. So I'll present my things in virtually. Okay, getting back to the presentation. We have a new network using deep learning. So we named it as FusionNet. Basically, we came the name by having time frequency information fusion for speech enhancement. So myself, Santhan, and I am from IIT Tirupati. Currently, I am pursuing my master's here in space processing and deep learning. So getting into the topic. Basically, speech enhancement main aim is to remove the given noise from a given speech signal. So it has got many applications in real world scenarios. Like it is one of the most pre-processing step in automatic speech recognition, and then it has been used in cochlear and hearing aid implants to make the speaker only listen the voice of the people, reducing the amplitude of background noises. And then it is also used to improve the quality of audio in mobile communications. So getting into the literature, this speech enhancement has been practiced since decades. Like there are many methods we can see for enhancing speech, like conventional approaches. If you see, Wiener filtering is one of the best in this field for removing the background noises, and then many adaptive algorithms like LMS, FXLMS, all these methods, and many statistical based approaches. They try to enhance the given speech, but they really perform well in synthetic data. And then maybe when it comes to real world scenarios where the noise was non-stationary, and then background noise will be non-stationary, and then the efficiencies is not meeting the requirements. So we must need a model that will efficiently works in real life scenarios too. So recent advancements in deep learning not only enhance the rest of the domains, it has also greatly evolved in the field of speech enhancement. So considering that, like there are many methods in speech enhancement. Like people used to follow many procedures to enhance the speech by using deep learning methods. Like first one, back in those days, people used to enhance the speech by only considering the magnitude spectrogram of given a noisy speech signal, and they will neglect the phase of the noisy speech signal, considering phase doesn't matter for the enhancement. So they will take only the spectrogram of magnitude spectrogram of noisy speech signal, and they'll feed it to the network, and they'll get the enhanced magnitude. Later they'll collect the noisy speech phase of the noisy speech signal and add it to the enhanced magnitude. That's how back then people used to do. And later studies reveal that phase 2 matters for enhancing speech. So considering that into mind, people started enhancing by considering magnitude and phase as well. So in that field, we got two new methods for enhancing. So one is by enhancing both magnitude and phase using direct raw wave as such, and then second one is enhancing the speech by using frequency. By using a complex spectrogram. These are the two ways that consider both magnitude and phase. So till now there are many existing methods in the field of speech enhancement that uses a deep learning method. But the existing state of art methods used either of the domains, like they might have used either frequency domain or like time domain for enhancing the speech signal, and with large number of parameters. And then they followed traditional loss functions like L1 or L2 for comparisons with the labels. So they try to enhance with that existing processors. So we in our checklist we thought of having a better architecture. So since we know that both time domain and frequency domain are complementary to each other, so why can't we have a network that blends both the information in a single network, so that it adds the information from time domain and similarly with the frequency domain. So we have this in mind, like we need to have a network that should have both the domains, and we should employ a loss function that should understand the network well for enhancing the speech. So with that checklist in my mind, we designed FusionNet. So FusionNet, we used FusionNet because it fuses both the information. Basically, we call it as a Y-net because of its shape. So it has an encoder and two decoder blocks, where one decoder deals with the time domain loss function, and similarly the second one deals with the frequency domain loss function. So we have a single encoder for both the decoders, so that while backpropagating like backtracing, we have both the time domain and both the time domain and frequency domain information in a single encoder. This was a main motto, so that encoder will become robust for any kind of C signal. So the network mainly comprises of instead of having common, I'll go to next slide so that I'll present it properly. So as you can see, this was a normal convolution layer followed with batch normalization and layer normalization and ReLU activation function. Later it is followed by dense block. So here dense block is having like 5 layers. In the dense block, as shown in the previous slide, we used to follow dilated and causal convolutions, which helps us to where dilated convolution helps us to increase the receptive field of the previous layers, and then causal convolutions helps us to prevent the leakage of information from the future frames. So this is how we designed. This is how the dense block was chosen, and then the dense block was present in each and every layer for both encoders and the decoders. And for upsampling, instead of transpose convolution, we used subpixel convolutions in order to overcome checkerboard artifacts, and that was the thing. And then that when coming to loss function, we employed time domain loss function in one of the decoder, and we employed a frequency domain, the loss function in the second decoder. So this is how this is an end-to-end network, and the input to the signal is a noisy wave of length. We considered a length of 16384 samples. We took the raw wave signal and we chopped it into 16384 length, and then when the n cross 1 16384 cross 1 and input signal is converted into frames with a frame size of 15 to 512 samples, and then frame overlap of 50%, which is 256 frames, and that's how we created a tensor of size 1 comma 64 comma 512. And later to the next layer, we using 1 cross 1 convolution, we increase the channels rate to from 1 to 64, and later on, and keeping all the channels and later on keeping all the channels and the number of frames constant, we decreased the frame size from 512 to 8 by using in the encoder part, and similarly we upsampled in the same rate by using suffix conventions. And once the encoded speech is collected over here, we have the enhanced speech signal, that too in time domain over here. We revert back into 16384 samples, and we used time domain loss function to compare over here. And similarly here we have the enhanced signal in frequency domain, but here in time domain, but here we converted the enhanced signal into frequency domain, where real and imaginary part, and similarly we converted the given clean speech signal into frequency domain with real and imaginary parts, and there we had a comparison with the mentioned loss function. So coming to loss functions, like starting we had L2 loss as loss function for both the domains, and the results were pretty good, but there is a chance of improvement over there. So later on the literature survey with super resolution domain, image super resolution domain, there people used to enhance the image by considering by considering Charbonnier loss function, where it worked very well. So we opted Charbonnier loss function from the field of image super resolution. There, the similar lines, we are also enhancing the speed, so it suits our task well. So the Charbonnier loss function specialty is it tries to behave as both L2 loss function and L1 loss function. So both L1 loss function and L2 loss functions has their drawbacks. Like L2 loss function couldn't able to minimize the outliers, and similarly L1 loss function couldn't able to minimize the loss at the edges. So this Charbonnier loss functions will act as both L1 and L2 loss function according to the situations. So we employed this for both time domain and frequency domain loss functions. So Charbonnier loss function for frequency domain is as follows. Like we compared real and imaginary parts as given. So here alpha is taken similar for both. So alpha here is 10 power minus 3, and later the loss functions, both the loss functions are combined with using gamma as hyperparameter. We have chosen and I'll explain a bit more in next slides. So coming to data set, so since for this we chosen widely used CSTR VCTK corpus data set, which is of this configuration. Like train set is around 11,000 samples with speakers with 28 speakers, and noises of 8 real and 2 synthetic SNRs 0, 5, 10, 15 dB. And then test set is similar to that, 800 samples with 2 speakers, noises of 5 different noises, out of 4 is real and 1 is synthetic. And then SNRs will be different from train and test, and test set is made sure that it is completely unseen from the train set. All this data set was downsampled from 64 kHz to 16 kHz. For coming to hyperparameter theory, we opted the Adam optimizer for stochastic gradient type of optimization, and we ran the complete network for 60 epochs with a batch size of 24, and we opted stepwise learning rate. So it will decrease once in every 15 epochs, starting with 2 into 10 power minus 4 learning rate, and the entire testing and evaluation was done on NVIDIA RTX 2080 Ti GPU, which is of 11, which consists of 4 graphic cards, each of 11 GB RAM. As shown in the previous slides, the train set converted into frames with 50% overlap, and similarly the test set is converted into frames without any overlap. So coming to results part, these are our results. So PSQ, which is a renowned we compared it with the existing state-of-art methods. These are state-of-art methods which have been in the market since a decent amount of time. These are some of the known matrices, including SSNRs. So our metric is like performed a way above of what existing matrices with about a good margin, about around 10% of increment in the PSQ matrix, and rest is good improvement in the rest of the matrix. So evaluation studies, we performed evaluation studies by varying different kinds of different types of loss functions for both the domains, and tested with only, and evaluation has been done with only one of the branches. Although there are good results with both the domains, for the time domain or testing with time domain branch has gave some cutting edge for results for us. So I can conclude that so comparative results has shown a good improvement compared to existing networks, and an improvement of around 10% in PSQ matrix, and an overall improvement of around 8% in the rest of the matrices. So these are some of the reference we found. Thank you.
Thank you, Santhan.
Yes, sir.
Have time for questions.
Do we have any questions in the audience? No. Also in the chat we don't have any questions. So Santhan, allow me to ask a question. Which of your branches performed the best, the time or the frequency domain one?
Sir, firstly we started with both the domains, and it performed well, but later on we checked with both the time domain and frequency domain branches, but we used to see the time domain has have some cutting edge when compared to frequency domain. So time domain is performing better than frequency domain.
Maybe I have also a related question. So the weighting factor gamma,
yes,
between the time domain and the frequency domain loss, did you set this? Did you fix this, or
no, sir?
You learned it, or how did you set it?
Yes, sir. It was we gave it to the network with right from the starting 0.5 bias to both, and it manually auto-tuned to I guess 0.8 to 0.2. For time domain it gave 0.8 to 8, and for frequency domain it gave 0.28.
Okay, thank you.
Actually, I have another question. You mentioned that you tried different losses. Did you also try the SDR or scale independent SDR, which is often used in time domain?
I note that point. I haven't tried, sir. I'll just check it.
Okay, thank you. All right, then let's thank the speaker again.